Well, hello everyone. I'm Mikhail Golovnya, Senior Advisory Data Scientist at Minitab. I'm making this video as a follow-up to my Predictive Analytics World presentation. We did run into some timing issues and all of that. I only had 20 minutes, so I had to rush over my presentation to deliver all of the key points. So what I'm going to do here, I'm going to take a little bit more time and go over the same set of slides and highlight all of the important parts of my message so that you can listen and you can learn, and we could have productive interaction on these matters. So as I have said, I'm Mikhail. I've been a Senior Advisory Data Scientist for, at this point, close to 2 decades. I started back in '99, and I've been exposed to all sorts of different algorithms in machine learning, data mining, data analysis, all these different things. I have seen different algorithms out there, and we all have our favorites. We all have different ways to work with the data and do all these things. But as we enter into the post-algorithmic world, it becomes even more important, especially if you want to advance your career in data science, to develop a deeper understanding of what algorithms to use, what data systems to use, and so on and so forth. And this is what I'm going to talk about: predictive analytics, the easy way. As we're trying to democratize machine learning and data science and the predictive analytics, there's this new need to develop a more solid understanding of the relative advantages and disadvantages of different approaches out there. So that's what I'm going to talk about: how to do predictive analytics the easy way. Now, several days ago, like yesterday, there was some discussions in the predictive analytics world about, okay, whether we should use logistic regression or tree-based techniques or gradient boosting or deep learning. So people are asking those questions, and I will give you one perspective here so that you can take at least something out of this from the perspective of data scientists who's being out there for several decades in various different industrial applications and financial applications, and teaching these things, developing algorithms and things like that. So let me start by first introducing a classification problem. And again, I could have taken some data set that is specific to a particular industry, but here let's just look at something that's simple. Let's bring in some kind of joy into our lives, because we're surrounded by these little guys out there, and it usually brings a lot of happiness to whoever owns them or sees them. And let's focus on the problem of trying to build a machine learning system that separates cats from dogs by assembling and knowing information about them. Now, if you were to focus only on the images here, you can understand the nature of the challenge here. So if you look at these two guys, our mind easily separates cat from a dog, but from the image perspective, it's not that easy. And the same thing could go here, have a cat and dog, or say here cat and dog, and so on and so forth. So there's something within our fundamental intelligent makeup that allows us to make these decisions. And historically, it's been a pretty challenging problem to tackle with, and only recently, with the advent of deep learning nets, a strictly image-based recognition has become more or less successful. But in addition to that, let's simplify this problem somewhat, and let me show you how you would normally approach it in a conventional kind of practical setting when you do not have access to all these server farms or something that is really convoluted and challenging out there. And the truth of the matter is, we start by assembling all these different features. Like, for example, in this case, we are assembling a bunch of different descriptors, we call them variables, that describe each individual animal. We assemble them into the table, and there's a one dedicated variable in the table that communicates kind. In this case, it's cat versus dog. So we only have two kinds, therefore this is a binary classification problem. And the objective of machine learning or predictive analytics in this case is to try to build a set of rules or procedures to separate cats from dogs based on the available features. Any predictive analytics problem out there will have something like this, regardless of the complexity, regardless of the domain expertise. This is the kind of stuff that you're going to have to work with. And there are many different ways we can address this problem. One classical way to address it, as a very favorite way among many practitioners out there, is known as a binary logistic regression. And it works like this. So we convert all of the input data into a table of numbers, or use continuous variables directly. Binary variables are usually represented as zeros and ones, and categorical variables are expanded into dummy indicators. Then we fit a straight line equation to maximize log likelihood, and we use the resulting equation to calculate the probability of being a cat or a dog, and it would usually look like this. So we compute log odds of, say, cat as a linear equation that identified some of the input features, and then we convert log odds into probability of being a cat, and this is all based on this potentially very large table of numbers. So this is the conventional way, the traditional way. And as much as I love logistic regression, and I understand that it fits certain areas of applications really nicely and really well, in this particular scenario with cats and dogs, I would call it a way of insanity, because you're really trying to mix all these different things together, and you're imposing a very alien framework onto the problem that's by its nature is not really that challenging conceptually. Now, it often happens to us when we use a wrong paradigm or something abnormal to solve the problem, and as we do it too often and repeatedly, what is not really normal becomes the new normal, so to say. And it sometimes takes time to unlearn and undo things that we have learned in order to see a different way to handle whatever scenario that you're facing at the current moment. So something like that happens in this case. Let's get back to the original problem and reanalyze it. There's a more intuitive approach. Instead of putting equations and log odds and all this other stuff that will make a lot of people roll their eyes, and of course it's a great job security for certain class of practitioners, let's address it in a more intuitive way, and that is by asking a series of questions. Like, for example, we might discover that if we ask a question, what's the lifespan of that particular animal? Is it longer than 10 years? If the answer is yes, we go on this side. And by looking into the data, we might discover that it turns out cats, on average, live longer than dogs. But it's not by itself enough to make the separation between cat and dog. So this is where we could ask another question here. And again, by looking at the data, do they have sharp claws? If the answer is yes, then we have a cat. If the answer is no, then we have a dog. And likewise, on the left-hand side, we could ask another question. Does it make a barking sound? If the answer is yes, it's a dog. If the answer is no, it's a cat. Now, notice the intuitive nature of this solution. Notice that it almost mimics how we often proceed in our heads and in our minds. Let's say someone told you that they have a pet, and let's play this little game. Let's find out whether they have a cat or a dog. Those are the kinds of questions that you can ask, short of course, asking directly whether it's a cat or a dog, right? So think about the intuition here. It makes perfect sense. And I can tell you, when you present this solution in a room full of business executives, it's so much easier to present it like this as opposed to, say, log odds and logistic regression and all the other things, because you're doing it in a natural way. Of course, if you were trying to present the solution to someone who already used to abnormal solution, let's say a reviewer in a magazine or something like that, someone like that, you may run into another trouble, but that's a story for another conversation in another video, okay? So a more intuitive approach. works like this. And it's one of the many. I'm not claiming that this is the ultimate way to resolve the problem here, but in the end, it allows us, in this case, to separate cats from dogs using a very straightforward, intuitive application that we can explain, use, employ, and show to someone else, and they will understand us too. Okay? So this brings me to the founding of what used to be Salford Systems, and then Salford Systems was acquired by Minitab. So now this is the legacy of Minitab 2, and that is the innovative legacy of the founders of machine learning. Back in 1970s and early 1980s, Bryman, Friedman, Olshan, and Stone, they were facing similar problems. They wanted to build an effective way to do a data-driven classification solution without pre-committing yourself to some artificial frameworks like logistic regression. Not that the logistic regression is a bad solution, is there's a certain number of applications where the logistic regression gives you the least intuitive representation of the problem of interest. Now, here's one such application that was found in those days in the military research. Suppose you have a radar, right? The radar was invented during World War II to fight against the Nazi submarines, U-boats. And the radar is detecting certain target on the surface of the sea or the ocean. It digitizes it, constructs the profile. So that was a really like a real life application when they needed to classify these profiles as representing different classes of ships. Okay, now here's what's interesting about this problem. This is a militarized version of a cats and dogs problem. Of course, here you have more than 2 different types, but that's just basically a more general way to formulate the same problem. And you can approach it from the logistic regression standpoint. You will have to deal with a lot of equations, coefficients, and all of these type of unintuitive ways to present it. Or you can approach it directly and say, okay, why can't we just build a classification tree, this hierarchical structure that answers a series of univariate questions about all these profiles, and then uses answers to those questions to classify all of these ships and to identify all of the different classes. And you know, the technique was so powerful and so interesting that it became known as classification and regression trees. And incidentally, it has become a de facto, like the #1 foundation for the entire category and class of predictive analytics techniques that make a lot of things a lot more intuitive and easy to represent, as opposed to all these other classes of algorithms out there. So this gives us a very good starting point, but let me move on and start describing different ways we can find answers to specific questions. Because remember, in the end, any predictive analytics problem is you want to find an answer to a very specific question, like what is going to be the price of stock? Is it going to go up or down? Is it going to be a failure or not? Is it going to be a good or bad outcome? Is it going to be cat or dog? Or is it going to be that class or that class of a ship, right? So one usual solution to this is when you have a question, you just ask an expert, and the expert, and in our case, expert could be a logistic regression model, or a classification and regression tree, or a support vector machine, or even a deep learner with some extent. Okay, but you're asking a question of a single authority and you get the answer. In many cases, that's all you need to do, and it works really well until you discover a situation that it is quite possible for certain class of problems to be so complex that single experts can be quite wrong. We've seen it happening more than once in the COVID era. There's a lot of experts out there, and sometimes I get the impression that every expert has his or her own opinion, and no one truly understands exactly what's going on, right? So betting on a single expert is actually pretty risky. That's why we can move to the next level, and that is when one expert is too much to commit to, maybe we could ask multiple experts. And then incidentally, if you start asking multiple experts, now you're leveraging the power of the crowd. You're kind of doing crowdsourcing. And you can ask either a limited number of experts, or you can even ask the whole crowd. You can generate lots of different responses and then rely on the wisdom of the crowds to get to the ultimate to find the most plausible answer. So you're asking multiple experts, they generate different answers, and then you can decide on the ultimate answer by either averaging when you deal with regression problem or voting when you deal with conventional classification output. Okay? Now, incidentally, if you take a single tree and treat it as a single expert, if you start asking multiple experts, what you will have is an equivalent of what we call random forest or bootstrap aggregation technique. And in this case, the technique was introduced by Leo Breiman and Adele Cutler in early 2000s. That was basically the final piece that Leo Breiman gave to the world before he passed. Okay? And then the idea is simple. We generate multiple trees independently. They don't cross-talk to each other. There's no connections. They're just grown independently, and there are many different ways you can do it. Either use bootstrap samples or repeat resampling or different chunks of the data partitions, or you can sample variables and other things, okay? So there are many different ways you can do it, but you grow them independently. So you generate this pool of independent experts / workers, okay? And then you induce differences by all of those techniques, and you make final predictions by averaging or voting. And this is how it's typically represented. So a random forest classifier, you start with the data set, and you run through these randomization techniques. You generate multiple, basically an ensemble of independent experts. Each expert votes for a specific class, and then you use majority voting or averaging for regression to either get the final class or the final predicted response, okay? So ensemble of trees is very powerful and conceptually generalizes asking multiple questions of a committee of experts, okay? Now, let me summarize what we've just developed so far. How do we learn? The simplest way is to approach a point of authority or an expert or single model and get the response. Now, in my case, that's a single tree, or it could be logistic regression, or it could be some other, it's like a single point of response in this case. Now, on the other hand, I've also demonstrated that you can generalize this approach into the idea of asking multiple experts or just crowdsourcing your question, ask the audience type of scenario. And in the case of trees, this is where you get random forest. And it's nice to organize these things in your head because, as I pointed out in the introduction, we live in the era when it's very important to understand the differences in different algorithms. You don't need to understand the individual kind of nuts and bolts of algorithms per se, even though sometimes that could be important to get the best tuning. But by and large, you really need to understand how we can leverage different approaches and where they're going to be strong and where they're going to be weak. So these are two ways: single point of query and response, and an ensemble of independent experts. Is there a third way? Is there a different way to learn? It turns out there is. Just like in real life, when you seek answers to certain tough questions, you can either question one expert, or you can question multiple experts, right? Like seek alternative opinions type of stuff. Or what? You can go to school and learn the subject matter and learn the answers to become an expert, right? And then I can visualize it in this following way. You start by going to school, and then you take a test. And based on the results of the test, you know the things that you need to learn more, and you take the test again, and then you learn more, and then take the test again. And hopefully, at the end of this learning journey, you will develop a set of skills that will allow you to find the answers on your own, okay? Well, guess what? This entire technique is known as a boosting technique. In the boosting technique, instead of generating independent experts, you're actually learning by gradual increments how to approach that ultimate prediction that you're interested in, how to zero in on your on the answers that you're looking for. So keep that in mind. Cart, random forest, and boosting, or we call it TreeNet and Minitab implementation, goes all the way back to Jerome Friedman. But what you will see, those are fundamentally different paradigms that you always need to be able to wrap your head around. So now that brings us to the question, okay, what's the implementation of boosting? Well, the stochastic gradient boosting specifically was introduced by this colorful individual. This is Jerome Friedman back in, I guess, in 70s, when he was still like a nuclear physicist and engaged in all these SLAC, Stanford Linear Accelerator Center and all of that, you know, risking the creation of microscopic black hole that could destroy the Earth, like suck everything in or anything of that nature. Well, I'm just kidding. But later in his life, Jerry looked in a more traditional academic way, so to say. And he came up with this generalization of what earlier was known as eta boost and introduced direct type of approaches into this whole structure to basically, I'll call it stochastic gradient boosting, also known as TreeNet, and that puts us again into late 90s and early 2000s, okay? So Jerry introduces that approach, and then later on there's a modified version of it is known as XGBoost. Very popular and open source out there, but conceptually it's just a different variant of the original Jerry's code. It relies on some additional second order approximations and all of this. The details are not that important as long as you understand in general what is going on, and this is still within the category of boosting. And as I pointed out, algorithmically, boosting can be presented as a series of weak learners that are linked together, where each subsequent learner is trying to correct errors of the prior combined collection of learners. So you're literally doing this boosting process, and then that's that school process that I presented on an earlier slide. Okay, so now the next big question then arises. Now that we have all these techniques, you have logistic regression, you have trees, you have random forest, you have gradient boosting. By the way, random forest is a no-brainer to implement. You just generate all these different trees in parallel. Gradient boosting is a little bit more tricky because you need to go over some algorithmic details and loss functions and probability surfaces and all of that stuff. Gradient components, Hessian components. But it's all doable. So now the big question is, who's going to be the winner? What is the best algorithm, right? Because that's often what we are interested in a post-algorithmic era. And here's what's interesting. Random forest versus TreeNet. I could set it up, visualize it as a match between Leo and Jerry. Battle of two distinct paradigms. One produces crowdsourcing. The other one is kind of guided learning. Who's going to win, right? So who's going to win? Let's put them in the ring. And you know what? That's what usually happens in real life. When you need to solve your problem in predictive analytics, you have access to these tools. But in the end, the ultimate arbiter is going to be the data that you work with. And you'll be surprised sometimes with the level of the different algorithms can handle your data. Now, when I talk about random forest and TreeNet, I often try to come up with the usual pictorial like visualizations. Okay, how can we describe the nature of the paradigm itself without being lost in all this algorithmic detail and all these other things that are literally not that essential at the end of the line. And here's one way to think about it. Get ready for it. The random forest can be visualized. We saw it on an academic level, but in practical level, I visualize it as carpet bombing. Okay, so we have a bomber that needs to destroy a specific target on the ground. It releases all of these different individual trees experts, whatever you call them, and then hopefully with enough volume and repetition, you will hit the target. It's very powerful, somewhat wasteful. A lot of resources are wasted, but if you use it on the right target, I mean, well, actually, it will do the job really well. Now, on the other hand, a tree net or gradient boosting can be visualized or conceptualized as a very sophisticated guided missile. All you have is one shot, but you have all these controls to guide it onto the target and get the hit. And you know what? In real life, it's almost impossible to predict which approach will work best. They're all equally powerful, albeit very different. Okay? I've seen it time and again when in real life, TreeNet would outperform random forest. And I've also seen other situations where random forest would outperform TreeNet. Now, sometimes you may need to monkey around with your target variable. Let's say sometimes even just a simple log transform of your target variable can bring the problem into the realm of TreeNet and allow TreeNet to outperform random forest. Other times it may not be that simple. It may not necessarily work. So the bottom line here usually it is witnessed by a lot of data mining competitions out there, including the Kaggle ones and other ones. Usually these two are strong contenders with each other. Now, I personally prefer TreeNet because I enjoy the sophistication of that algorithm and I enjoy the level of fine tuning and controls that gives you. But hey, in many scenarios, random forest will do the job equally well. It may be bulky, it may be not as efficient, but you can do it in parallel and you can unleash that firepower to cover your target either way. So keep that in mind. I kind of find it funny that we started with the cutie, these cats and dogs, right? These cute pets and animals, and we ended up with carpet bombing only within, what, a span of 20 minutes. Well, such is the nature of the world that we live in. Speaking of which, why do we need predictive analytics? Let's say if I were to pitch predictive analytics to someone, and especially these new powerful sophisticated algorithms like TreeNet, random forest, deep learning nets, etc., etc. Why do we need predictive analytics? Well, usually it boils down to three different dimensions, so to say. We want to build more accurate models. And in many business scenarios, more accurate model means more money or less risk or bigger success or anything of that nature, right? Accuracy directly converts into business value. Or we want to understand what is going on. And we want to understand what is going on. We're not necessarily focused on accuracy, even though getting better accuracy always helps, but we want to understand what the story is there. And I can tell you, these guys, they work in a different ranking. Like on the accuracy side, usually, not always, TreeNet or gradient boosting models, they shine, followed fairly closely with random forest. Sometimes they flip. Followed by trees, followed by classical models. And again, in classical models, the skill of the analyst is paramount. If you get the right model, not enough data, classical model can shine. But in these large data scenarios, classical models, they usually cause the biggest grief and the biggest concern and the longest amount of time that you'll have to spend. Now, on the other hand, if you want to understand what's going on, interestingly enough, TreeNet still gives you some very powerful ways and means to deliver the insights, which is not shared by random forest. And in a few minutes, I'll show what I mean. On the other hand, trees, as you saw in the introduction, a single tree gives you a pretty decent, plausible story. It's not the ultimate story, but it's a great start, and it's a great way to entertain a lot of people and a lot across the departments who want to understand what's going on. Okay, so the classical models, as I've said again, they're very finicky with settings and underlying assumptions, but that's why I put them there, followed by random forest. So those two cover a lot of scenarios, except if you're on the sales side, never underestimate the factor of vanity. There's sometimes people just want to have something because everyone else has it. Whether they need it or not is another question, but it's certainly cool to have access to that feature and that feature and that feature, and that's why I put it here. And again, to summarize, we live in the fallen world, so to say, and this world is driven by money, power, and vanity, and that's how all of those three things, they can be summarized. You either have money, or you have knowledge that leads you to money and power, or you're just consumed by vanity. And again, it doesn't mean that I like it. It doesn't mean that we should be happy about it. But hey, I'm just giving a diagnosis. And whether you like it or not, it doesn't change the nature of the objective reality. And we should always keep that in mind. Now, we can either go about it and do bad things or go about it and do good things, but that would be the whole other story here. Okay, so let me finish this with something that is actually good, and that is the use of a solar power to generate electricity, right? Like I live in San Diego, California. Sometimes I remember several years ago when I first went to Vegas and I saw these massive solar power plants. It looked almost like I was in an alien world. I was like, wow, what is that? That is something totally immense and intense. But the solar energy, in some senses, it's a going back from power that we can't control to the power that is at the mercy of nature, right? Now, you can still predict certain things about nature. Certainly in Las Vegas, you have most of the days are sunny, so you can predict the position of the sun. You can do weather forecast and so on and so forth. But still, you're not in full control over this thing as opposed to more conventional power generation facilities like gas, oil, coal, and things like that. Okay, like you can run your own generator and have full control over the generation of power. You cannot have that full control when you're at the mercy of the solar. So in this particular scenario, what we were interested in is building a model that allows to predict energy output of a solar plant as a function of time of day, sun elevation, and all these different weather characteristics that can be predicted. So this way, when you put that power plant within the power grid, whoever maintains the power grid, they can estimate the level of power being generated so that they may not necessarily run into trouble the way it happened a month or two ago in Texas when they had this massive statewide blackout. Okay, so as we move into these nature dependent type of technologies, it becomes more and more important to make accurate predictions. And in this case, we want to predict energy output in kilowatts. So like, for example, here, by the time it's 9 a.m., the energy output is actually 1.5 megawatts. So it's a kind of it's like a typical size solar farm that can feed, let's say, like 30 to 50 homes with a conventional power consumption limit. Okay, so it's not something major, but it's a useful unit of operation. So we want to predict energy output based on these characteristics like time of day and weather variables. Okay, so here is what happens if you now, as a data scientist, you know what the problem is. Now you start applying different algorithms. Remember, it's post-algorithmic era, but it doesn't mean that we shouldn't worry about algorithms themselves. We just use them as individual units. So here's what happens. If you apply classical regression, you get this type of linear equation there, and you're going to make about 78% accuracy. So this is as far as that linear regression of the box without further tinkering and investing your time and effort into all these fine details. This is how much it can give you. Okay? Now, on the other hand, if you run it through a regression tree, and it's just a matter of switching from one to another. Again, you just picked a different algorithm. If you run a regression tree, you get 34 terminal nodes tree. This is a regression problem in this case. And your test performance in terms of R-squared is 79%. Not a major improvement compared to classical regression, but a fundamental change in the paradigm. Now you're looking at the tree, at the segments, and all of this, okay? So the third method is you can unleash random forest. And again, it's just picking a different algorithm. Now, if you do the committee of experts, a striking thing happens here. The performance moved dramatically from 79% up to 87%. That's pretty much, 8 points increase. That could mean a lot of money. It could mean a lot of other things, okay? So it's a non-trivial amount of improvement. It shows clearly that random forest outperforms classical regression and the single tree, as a matter of fact. So you have the leveraging of the committee of experts in this case. And finally, if you do, so the random forest was carpet bombing, right? Now, if you do the guided missile, the tree net or gradient boosting, what do we get? Well, in this case, we're actually getting even slightly better performance, but not by much. So in this particular scenario, random forest and tree net, they pretty much exhibit similar levels of performance, but they do it in a very different way. So from the formal point of view, tree net is the absolute winner, but the random forest is literally behind by a hair, right? And then there's a huge gap between these two that are always trying to compete with each other, to contend for that winning position. These are followed by regression tree that gives you a very cool kind of graphical description of what's going on, the simplified structure, simplified story, followed by classical regression, which in this case just receives the participation medal, okay? Because clearly, without further work, it's not capable to compete with these power lifters on this side. Now, when you look at random forest and tree net, my personal favorite is always the tree net. And the reason for that being is that it not only gives you good and excellent predictive accuracy, but it also explains what's going on. So if I move to the next slide here, tree net gives powerful insights, okay? It gives you ranking of all these individual inputs according to their performance and a contribution to the model. And it also shows you individual contributions, okay? So for example, if you look at the sun elevation, you'll see that when the sun is below the horizon, there's basically zero output, and then it enters into this transition form until it reaches the maximum around here when the sun is at the highest point, right? Similarly, cloud cover. If you have very little to no cloud cover, your energy output is at the maximum with respect to this input, and then past a certain point, past basically 50%, when half of the sky is covered, now you experience rapid decline in the power output. And again, look at these individual scales. Sun elevation is the #1 driver. That's why it's presented here. Cloud cover is the second one, followed by wind direction, followed by sun direction. So now you can see how the tree net not only gave you the best top accuracy, but it actually explains what's going on, and it even gives you two-way plots in the heat maps or 3D plots and that type of level of insights when you can spot potential interactions or other things that are often of interest. And I can tell you this, combined with the power of the predictive accuracy, is a killer combination. And you don't waste as many resources because remember, it's a guided missile and not a carpet bombing the way the random forest is. So as you can see, this is the post-algorithmic era of predictive analytics. You don't have to do everything using deep learning nets or some farms of servers or sophisticated stuff. There's a whole class of practical problems that can be very easily handled by these power tools, and Minitab offers these tools to you, and you don't have to spend too much money and resources to start getting these results right away. And it's just as simple as picking different algorithms, unleashing them into your data and seeing how well it performs. And I can guarantee you, in my 20 plus years of being a data scientist, and I've seen all these different tools and techniques out there, my personal favorite is always this power combination: regression or logistic regression, decision trees, random forest, and gradient boosting. Sometimes I use them all. Other times I can go, say, from decision tree to identify the general features, and then straight into TreeNet to identify the fine features. And there's some scenarios I take the insights obtained by TreeNet, which you get basically the predictors that are driving your signal and the nature of that dependency. Now it's a no-brainer once you see these plots to convert them into nonlinear transformations and then go back to classical regression or logistic regression and leverage it all up, so to bring the level of performance on par with random forest and TreeNet, while at the same time keeping the simplicity of the underlying structure. And that is what I mean by when I say machine learning or predictive analytics the easy way. With these tools, you can genuinely do it the easy way. As a data scientist with experience, I can do Python, R, I can do programming in C++ and all of this. Those are all powerful techniques and tools, but it took me years to develop that skill. And do I want to use it every single day? No. No, I want to have access to tools that make all the job a lot easier for me as the data scientist. And I'm pretty sure many of you do not have either desire or resources to do it the long way. But by having access to all of these tools, you basically pushing yourself to the whole new level of capabilities and performance without wasting your time on getting there on a long learning trajectory and the learning path. Okay? So take it, use it, enjoy it, and you will see your life is never going the same as analyst, as a data scientist, and the things that will become possible will blow your mind. Thank you.